Hello folks, today we're talking about properties of determinants. This is material from 3.2. So I just want to recall the setting here. If let's say A is an n by n matrix, a square matrix, then we have this thing called the determinant, det A. This is a number, let's say with useful properties. So we talked about some of these last time. I want to go over some others today, remind you of those other ones. The main question I want to ask today is how do row operations affect the determinant? Okay, so as you know, there's three flavors of row operations you can perform on a matrix, and I want to know if I do one of those to a matrix, how does the determinant change? So I'm just going to basically tell you and maybe say a little bit about why. So let's say, suppose A is an n by n matrix, and B is obtained from A by, let's see, so there's three things we can do, right? The first thing is our favorite one. We can replace a row by the sum of that row and a multiple of another. All right, so this is our kind of favorite row operation that we use to clear above and below pivots. Then it turns out that the determinant of this new thing is actually the same as what you started with. So it doesn't actually change the determinant. That's pretty nice to know. What else can you do? You can also exchanging two rows, right? Row exchange or row swap. Then it turns out that the determinant does change. So the determinant of this new matrix is minus 1 times the determinant of the matrix you gave me. So it does change the determinant, but in a predictable way. And finally, we can scale a row by, let's say, a number r. Then it turns out, again, it changes. The determinant is now r times the determinant of A. So I guess to make this grammatically correct, this should be replacing. Right? Okay, so these are the three row operations. Well, in one case, they don't even change the determinant, but in these other cases, we know exactly what they do. I'm just going to say that I'm not going to really tell you why this works, but the way to prove this is you check that this works for 2 by 2 matrices. And this is actually something we're going to be doing on the worksheet. And then what you do is you use something called mathematical induction. And the idea there is that, well, remember that the determinant of a matrix of an n by n is defined recursively, where you keep taking these smaller determinants to compute. And so if you assume it's true for a 2 by 2, that'll tell you that it works for a 3 by 3 when you apply the formula. And then, well, to do a 4 by 4, you break it up into 3 by 3s and et cetera. Okay, so that's the idea behind induction. I'll let you check the book for the details. But let me show you how this might be applied in practice. So, for example, let's find the determinant of let's say A, I'm going to do a 4 by 4. So 2 minus 8, 6, 8. 3 minus 9, 5, 10. Minus 3, 0, 1, minus 2. 1 minus 4, 0, 0, 6. Okay. So this is a 4 by 4. Now, of course, you could, before this lecture, you could compute the determinant by using your usual formula where you pick a row or a column to expand upon. I want to show you how row operations can actually be employed here. So what I want to do is, well, my usual story, I want to get this thing to an upper triangular matrix by my row operations. So what I'm going to do first is scale that first row by 1/2, because I want to have a 1 up there just to make my life easier. So this is 1 minus 4, 3, 4. I won't touch this row or the third row or the last row. So let's call this matrix B, right? Now what do I know is, well, I scaled this row by 1/2, so what I know now is that det B is going to be equal to 1/2 of whatever det A is, right? A is the matrix you gave me. I got this matrix by scaling by 1/2, and this rule 3 says that the determinant also scales by 1/2. Okay, so now I'm going to clear below this pivot. So I leave that row alone. And this is minus 3 times that, so this is going to be 3 minus 4 minus 2. I'll take 3 times the first row, add it to the third. This is 0, minus 12, 10, 10. Hopefully I'm doing this right. Then I'm going to take minus 1 times the first row, add it to the last. 0, 0, minus 3, and then 2. Let's call this C. Now notice the only row operations I did were these type 1, where I replace a row by the sum of itself and a multiple of another. And so that doesn't change the determinant. The determinant of this matrix is actually the same as the determinant of B. Okay, well, what I do now is I'll clear below this pivot. I'm not going to scale it. I'm going to leave that row alone and just clear below it, right? Because I can take 4 times that guy. And, all right, that's a 2 there. And then I'll leave this as it is. Let's call this matrix D, and again, the determinant of D is the same as what I had before because I only did one of these type 1 row operations. Okay, and finally, let's clear below this pivot. I'm not going to scale it. I'm going to leave it as it is and just take minus 1/2 of that entry, right? So that'd be 0, 0, 0, and then this will be, let's see, minus 1 plus 2 is 1. Okay, so if this is E. Now what I know is that the determinant of E, again, is the determinant of the previous matrix D, but also I know that the determinant of E, since this thing is, right, upper triangular, it's just the product of the diagonal entries. So what are the diagonal entries? It's 1 times 3 times minus 6 times 1, which is minus 18. Okay, so minus 18 is the determinant of this because, again, it's triangular. And then if you go back to what we wanted, well, the determinant of A is twice the determinant of B, which is the determinant of C, which is the determinant of D, which is the determinant of E. So this will be twice times minus 18, which is minus 36. Okay, so again, if you go and check this determinant of A that I gave you, you'll get minus 36. This is probably not any quicker way to do it, but it just shows you how row operations can be brought into the game. Okay, now what else do I want to say? Well, it turns out that this, knowing these facts about the row operations and determinants has other nice applications. So let me write this as a fact. Well, suppose, based on what we just did, suppose A has been put into, echelon form by only these type 1 and type 2 row operations. Okay, so remember type 1 and type 2, this means that no scaling. I haven't done any scaling of any rows. Then, well, if you just go back to what we did here, I did scale, of course, here, but starting from here I didn't scale. And notice that when I get down to the echelon form, what I get is a determinant that's just the product of those diagonal entries. So what I can then say is that the determinant of A is actually equal to, well, it's minus 1 to some power, depending on how many swaps I had to do, times the product of the pivots. This is if A is invertible. Because remember, if it's invertible, it will reduce to the identity matrix, meaning that the pivots will be down the diagonal. Now, if it's not invertible, right, that means that there'll be a 0 on the diagonal entries, and so when I take the product of the diagonal entries, I get 0. So this is if A is not invertible. Okay, so again, this is just more or less recapping what we did in that example, just for the general picture. But any matrix can be put into echelon form this way. I mean, remember, you guys are experts at row reduction, and the only time you scale a row is to, for your convenience. So you don't have to do, you don't have to deal with fractions, but you can always put a matrix into echelon form by just these kind of type 1 and type 2 row operations. So what this implies is the very useful fact that we already saw in the previous lecture, but I want to write it out again, if A is an n by n matrix, then A is invertible if and only if the determinant of A is not 0, okay? And so that's just a, again, a corollary of the statement here that says, if I put my matrix into row echelon form, I can exactly tell you what the determinant is, well, I can tell you it's the product of the pivots, and therefore it's going to be 0 or non-zero if and only if it's invertible. Okay, so last thing I want to just talk about briefly is another kind of application of row operations. So row operations and matrix multiplication. So recall now that, right, so from last time we saw that row operations can be encoded by matrix multiplication. So suppose E is an n by n matrix that performs or represents or performs a row operation. So this is something we talked about last time, that I can write E times A, and this matrix, right, this thing that is multiplying A, right, does that row operation. So just for example, if you did E was something like this, this is a -2, 0, 0, 0. This is the thing that replaces row 2 with -2 times row 1 plus row 2. This is type 1. Then it's not hard to see that the determinant of E is equal to, well, it's 1 if E is a type 1. So I guess we call this a row replacement. It's going to be -1 if E is this type 2 row exchange. And then finally, it's going to be R if E is this type 3 row scaling by R. Okay? And so these aren't hard to check. I mean, just if you write down what the matrix look like, right? So this is a triangular matrix, and its diagonals are all 1, so of course its determinant is 1. And it turns out that this is, this is 1, 2. I'm not going to go through the details here, but this actually implies this other fact that if you take two matrices, or n by n matrices, then the determinant of the product of those two matrices, right, this is going to be another square matrix. You can take its determinant, and it's actually the product of the determinants of the matrices you gave me. Okay, and again, I'll let you check the book to see how this fact that I kind of sketched up here can actually be used to prove this fact. Okay, and I think I'll leave it there. We'll talk more about determinants next time. I'll see you then.